Hello my friends, this is lecture 6, electric potential. Main idea here is to understand electric potential and electric potential energy and use them to apply conservation of energy. We learned that there's an electric force, and the electric force is applied by electric field. If we have a charge, there's an electric field around it. Electric potential will be related to electric field. So if there's separation of charges, this would be symbolized in our parallel plate capacitors. Actually, we said there's electric field from plus to minus. This guy would be field. And there is also a potential difference in between. We call this in daily life voltage. So you heard about voltage. That's the potential difference. We express potential difference using potential energy, electric potential energy, very similar to taking a book and lifting it up. We take it to a high H, we will give it a potential energy because we're pushing it against the Earth's gravitational pull, gravitational field G, and we will have a potential as mgh. Or similar to pushing a spring, compressing it, amount of x, we give it a potential energy. That potential energy is equal to 1 over 2kx squared. Because we're doing a work against a force, we are storing energy inside these two objects. Very similarly, if I have a configuration of charges, positive charges, I push another positive charge from some distance to closer to them, I am doing a work. If you do a work, you store energy, and that's the potential energy. We store potential energy. Since it involves electric forces and electric charges, it will be electric potential energy. We learned that in the electric field model, that if there is a charge or a charge configuration, although there is no test charge to feel the effect, there is an electric field effect around these charges, and we showed it as electric field lines and so on. And we said whenever we put a charge into this electric field, it applies an electric force to it, and we can easily calculate that force. Electric potential energy and electric potential are also related in a similar fashion. If we have a charge configuration, there is a potential, electric potential around them. And whenever we push a charge into this electric potential, we store energy in it and we give it an electric potential energy. And that energy becomes U electric. It turns out that if we have the electric potential energy and divide it by charge, we will always find a value at the same point. We will find a value that is always the same for different charges, and it will be electric potential. In a different fashion, we will use a V for electric potential. I'm going to put in this line here for potential, electric potential, so you guys won't be confusing it with the potential unit, which is volt, also V, and velocity. For velocity, we will generally use small v, but it's still possible to confuse. So this is the value we calculated. We call this V. And from here we can easily see that we can calculate the electric potential energy by multiplying the charge by this number that is associated with each charge we use to put into the same point there. So we can rearrange this as QV. That's electric potential energy at a point of a charge. And here it is summarized. So electric potential energy is equal to QV, and it's very similar to electric force being equal to Q times E. I have charge configuration. I know what is the potential at some certain points. I put my charge at some certain points. I will know what is the electric potential energy of that charge at that point. This problem will come back to later. I'll look at quick questions here. Two charges are brought separately into the vicinity of a fixed charge plus Q. First plus Q is brought to point A, a distance R away from this point. Second plus Q is removed and minus Q is brought to the same point A. The electric potential at point A is the greater for minus Q charge in situation 1, greater for minus Q charge in situation 2. Electric potential at a point does not depend on the charge we're bringing in. So it's the same for both. Potential energy, though, would be different. So if it says electric potential energy at the point A is to decide that I look at how much work I am doing. And we won't be quantitatively calculating it. Thinking about, as I bring this charge here, I see my hand here, I'm holding on to this charge and bringing it. How much work I am doing. We know that plus pushes on plus, so this guy will be applied and against force always. It will change as I move closer, but it will be applied. And this charge will be actually pulled. I don't even have to do my work. So I do a lot of work here, right? Not much work there. Then the potential energy will be greater for plus charge. Can I calculate those? Yes, I can. I will say U is equal to Q times V, and effect of charge is the same charge Q, so there will be same potential difference here, potential here, same potential there. For plus charge, I'll have plus QV. Let's put here plus. For minus charge, I'll have minus QV. And guess what, my friends? Energy is not a vector, is a scalar. Plus minus shows strength. Not like vectors. For vectors, plus minus shows direction, and the length of the vector is the strength. For a scalar, energy, plus minus shows the strength. So negative value is smaller than positive value. And I can imagine why I'm getting a negative work here, because I'm not even doing a work. My work is negative because the pull force is already doing that work. The electrostatic force is actually pulling it and doing this work for me. That's why I'm getting actually negative work. It all makes sense. And it's smaller than positive. I'm not really straining myself there. Sources of electric potential. We kind of actually already learned if we have charges, we have electric potential, but they could be like here, they could be like capacitors plus minus separated, then we will have a electric potential. If there is no charges causing that, there is no electric potential. There are many natural causes causing a potential as we scrub our feet to a carpet, we get charges, generally negative charges. When we go to close to a knob, there is a potential difference, what we call delta V, and we will have zap, and charges will move towards the knob. There are clouds we already talked about. Charges separates, as in this example here, maybe minus charges down, plus charges up, and they will induce charges on the ground that will generate kind of parallel plate capacitors, and we will have a potential difference here. It will cause an electric field, plus to minus. If this electric field is large enough, it won't be, of course, uniform as in capacitors, but we'll have overall an electric field. And as this electric field increases, charges increases and increases the electric field, potential difference also increases, and we have strong enough potential difference to ionize the air, meaning electrons are separated from the molecules in the air, and these charges makes a path through the air and flows down into the ground, which is what we know as lightning. Lightning very similarly can happen in the volcanoes, where there's rubbing in between the molecules and objects, ash in the cloud. We have a light negative charges going up, positive charges staying down. We have charge separation. We will have a potential difference, and it will also cause similarly lightning. Cells can have a potential difference through their working. They can have a charge separation, different charges on this side and this side here. Overall it's minus 70 millivolt. Naturally, and we can have a what we call potential difference of voltage, and we plan to have a potential difference to use in batteries. We use generally chemical separation of charges, and we separate charges of plus and minus inside the battery, so we can use this too. We'll see in the next unit in the system, to move our charges always, and as the charges moves, we'll see what will happen, right? We will have light and so on. I'll go this part quickly. Generally, we can measure electric potential using devices. Nowadays, we generally use multimeters. Simply, we put our device to one and the other end of the potential difference, and you can see in our device. This is called voltmeter if I'm using my multimeter as a voltmeasure, and we'll talk about these more. Here, an interesting picture here is there's a nerve cell, and they are measuring the potential difference with this device here, what is called a pipette, micro pipette. Electric potential can cause charges to move. Similarly, it's a way to understand actual electric energy. So we separate charges, right? When we separate charges, as you may remember from previous lectures, we have charge separation, we have electric field, plus to minus. So these yellow lines are here, electric field. This very same charge separation also again causes a potential difference. When there's a potential difference, there's electric field and charges moves. So if we put a charge inside potential difference, they will move, and positive charges always moves from high potential to low potential. Here the positively charged plate, this is actually a parallel plate capacitor, is high, and negatively charged plate is low potential. So positive moves down, high to low potential. We also know this through positive charges are applied F force in the same direction as electric field. The same idea still works here. And negative charges moves against, or negative charges applied a force against the electric field. Now we can imagine what happens here as these charges moves. They gain or lose their kinetic energy. If I think logically, if I leave this positive charge without touching it, it will be pushed down, right? And it will gain kinetic energy, gain a speed. So kinetic energy increases in this direction for positive charge. Imagine I'm pushing it in the opposite direction. What happens then? I have to push it, I have to do a work. Or let's say I throw it upward and let it there. It's trying to go upward, but there's a force downward, so it will be slowing down. If it's going upward, kinetic energy will decrease. And what happens is I have to do a work to push it upward. I store potential energy in it. Opposite happens for negative. Negative is naturally pushed up. As it goes up, it will speed, its kinetic energy will increase. But imagine if it wants to go the other direction, we have to push it to let it go. We will be storing potential energy in it, and if it has a kinetic energy, it will be slowing down and decreasing. We can calculate how much kinetic energy changes if it increases or decreases using conservation of energy. And conservation of energy simply tells us that initial energy of any type is equal to final energy if the energy is conserved. Here we will have electric potential energy and kinetic energy. So what we will say, final kinetic plus final electric potential energy is equal to initial kinetic and initial electric potential energy. Then we put in all the values. We know kinetic energy is equal to 1/2 mass times the speed squared, and electric potential energy, I'll call it UE for short, is equal to Q times V. If I'm looking for initial, I call this initial. If I'm looking for final, I call this final. So this one equation I can use here. We won't be concerned with other types of energies and losses due to friction and so on. So mainly that's what we want to consider here. That's one way of solving values using energy conservation. A shorter version of that would be this. Total change in kinetic energy is equal to minus Q charge times the change in potential energy. When you work this out, you will see that that's what it gives you here. Take this guy to the other side. This guy goes as negative, and it gives us this. We don't have to derive it. I highly suggest to use this equation solely, drop the others, and work around to find answers. This is simply summarizing similar idea again for positive charge. I'm starting at 500 volt, going to 400 volt. So I'm going from high potential to low potential. Its kinetic energy will increase and potential energy will decrease. If it goes in the other direction, low to high, the other way around, it will work the other way around. Now kinetic energy will decrease, electric potential energy will increase. Let's also put this here. So what it says here, when a positive charge moves from a region of high potential energy to a region of low potential, high electric potential to low electric potential, its potential energy decreases, its kinetic energy increases. The first case here. When a negative charge moves from a high region of electric potential to a low region of electric potential, a region of low electric potential, its electric potential energy increases and kinetic energy decreases. I'll just say here, opposite happens for an electron. It's negative charge. If it's moved from high, let's put here a negative charge actually. Maybe make it blue. So I am putting the blue signs for the negative charge for an electron. It's, let's say it's going from high to low potential. Its kinetic energy will decrease and electric potential energy will increase, opposite to what happens to proton. And the same here, opposite happens for the electron. So I put an electron in the low potential, move it to this direction to a high potential. What will happen is what happens to opposite to what happens to positive charge. Kinetic increases, potential, electric potential decreases. To be able to remember that, you don't have to memorize this, you can come to this page always, but to be able to remember, always assume the low potential side is kind of a negatively charged side of a capacitor, and high potential side is positively charged. You can imagine as electron moves, it's already pushed here, kinetic energy will increase, thus potential energy will decrease. And positive should be losing kinetic energy because it's going against the force, electric force applied to it. This is summarizing what to do to solve for these type of energy conservations. I highly suggest using total K, change in K, kinetic energy is equal to minus Q times total change in potential energy or electric potential energy. We're going to look at this question later, but idea here, we have a proton, we put it here, it has a speed of this. It's going this, let's call this V initial, V final, going from a 1500 volt to minus 500 volts, so it's going from high to low. And what happens to its speed? What is its final speed? That's the idea here. Delta K, change in kinetic energy, is equal to minus Q times the change in potential energy. Oh, sorry. Let me go back here. Did I have to change that to change in potential energy. That's right. But change in potential energy is Q times delta V. Let's rewrite this. Delta K is equal to Q times delta V. And the same here. Oops. Undo that. Just delete this part. And Q delta V. We'll work on this in another video. Let's do the quick check. So a positive charge moves as shown, its kinetic energy. What happens? Think about if it would move this direction easily by itself, or we have to push it. If we have to push it, kinetic energy decreases. If we don't have to, kinetic energy increases. We have to push because we have positive charges here. There is a force applied in the opposite direction, right? So we have to push it with our hands. We have to do our work. If that's the case, kinetic energy decreases, electric potential energy increases. Going back to what we discussed, low potential to high potential, kinetic energy decreases, and potential energy increases. But going by the logic of force, and if we have to push it or not, actually is an easy way of looking at this. So kinetic energy decreases. A proton is released from rest at the dot. Afterward, the proton, so let's see here, we have a positive charge, right? Proton, this is low potential, this is high potential, low to high. It doesn't go from low to high naturally. You can also again imagine in low there are negative charges, in high there are positive charges, and this guy will be pushed in this direction towards the low potential because of these forces, or pulled by these guys over here, so it will go down. If we leave it there, moves downward with an increase in speed. Why increase in speed? It gets closer and closer to here, or we say its kinetic energy increases. If a positive charge is released from rest, it moves in the direction of the lower electric potential. We did several questions on that already. This is just about electron volt. It's a unit of energy that you didn't learn before. Now, electric potential, we said QV, it's, if you look at the units, let's do this in a different way a bit. Q times V. If we look at the units, this is volt, this is coulomb, this is volt time coulomb, that's joules, the same as joules as we learned in 151, energy unit, SI, unit for energy. There's also another easy unit for calculating this. For charge, we know 1E is equal to 1.6 times 10 to minus 19 coulomb. Instead of taking the charge as coulomb, I take the charge as E. So unit of charge can be taken as E. And we know what is E. It's 1.6 times 10 to minus 19 coulomb. And Q delta V, instead of using coulomb here, I can use E. QV, sorry, I can use E. Delta V is the same. And volt. So I'll have E times volt. If I take that as unit of E, E times delta V will be EV, and we call this electron volts, because E is the charge of an electron. Description of an electron volt is, if we leave an electron from a negative plate, it will go to the positive plate and gain an energy, because this negative plate pushes it, right? And positive pulls it, the same idea. If these plates has a potential difference of 1 volt, the amount of energy this electron will gain will be 1 electron volt coming from Q delta V. That's the description. The energy an electron gains by moving through 1 volt potential difference. If we need to convert, we can always calculate the energy in EV, and when we need to convert it, we convert to joules using this conversion formula. So 1 EV, 1 electron volt is equal to 1.6 times 10 to minus 19 joules. Let's look at this question as the last thing here. We have proton. 2 protons, sorry. One we let go and it goes in this direction. This is proton 1. And one goes in this direction. Proton 2 from the same point. They follow these trajectories. The proton speed at point 2 and 3 are related by which of these? And here it could be confusing if I look at their path. Their paths are quite different. But I'm going to look at the potential difference they go through. Is that I have a potential here, initial potential, and I have another here, final potential. And delta V they go through is the same. Now they both have, let's say, zero initial speed. I was just checking to make sure that the question says with the same speed initially, which is important. So these are the same. And we know this equation, delta K, change in kinetic energy, is equal to minus Q delta V. These are protons, same charge. This is K final minus K initial. They have initially same velocity, so same initial kinetic energy. Let's say these were 0, so kinetic energy is also 0. Then final kinetic energy is equal to 1 over 2 mv final squared is equal to minus q delta v. If I work this through, then I say, oh, okay, they should have the same speed because they both are protons, mass is same, and this part is same for both, so both will have the same speed. This should be the answer. But there will be some difference. This guy probably will take longer time to get there because it has a larger path. That doesn't change the result that it will have the same speed here, V final. Not speed, yes, not velocity though, because they have different direction. Magnitudes are the same. Alright, I'll leave it at that and I'll see you in the next lecture. And think about this question.